Chemical Equilibrium Part 5, Ice Tables and Equilibrium Calculations. Okay, so before we actually get started, let's just remind ourselves of the law of mass action. So we have our generalized reaction and the equilibrium constant expression that is related to the concentrations of products and reactants in this way. So we are going to start using this relationship now. And what we're going to find out is that it's possible to calculate the concentrations or partial pressures as required of reactants and products at equilibrium. So if we have the value for the equilibrium constant K, then we're going to see that we can use an ice table to figure out what these equilibrium concentrations or partial pressures would be. So that's what we're going to learn to do in this video. Now, ice tables are actually not required for equilibrium calculations, but they are a very convenient way to organize all the information and variables for your equilibrium calculations. And the way that we set them up, we write the reaction that we're looking at the top with the equilibrium arrows, the double arrows, and then we label 3 rows, one I, second one C, third one E. And so I stands for initial, and what that means, those are your initial conditions. C is for change, and so that is the shift that the reaction is going to take on its way to equilibrium. And we'll see how to apply that. And finally, equilibrium is what we have at equilibrium. Now, in various problems, sometimes you'll be given initial conditions, and that's what we're going to look at. Other times you'll be given the equilibrium values at the very end, and you have to figure out what the initial conditions were. But you always have a way to do that if you use an ice table and you set up and organize all of your variables. It helps you to see what you need to do in order to solve the problem. Okay, so the first thing that you do when you start an equilibrium problem is write an ice table like I have here, and fill in what is known or not known about the initial conditions, the direction the reaction proceeds, and the conditions at equilibrium. And I always start by writing the reaction at the top and then ICE. So when you start an equilibrium calculation, just write that down. And then we're going to see how to fill it in and use it. Now, after we have drawn an ice table, and we fill everything in, we're going to be able to solve for those concentrations or partial pressures of reactants at equilibrium. And so the big question is how? Just reminding ourselves, so here's our reaction, nitrogen dioxide in equilibrium with dinitrogen tetroxide, and our equilibrium constant expression in terms of partial pressures is here, and it's products over reactants. So partial pressure of dinitrogen tetroxide to the first power, because that coefficient is 1, and partial pressure of nitrogen dioxide to the second power, because that coefficient is 2. And so what we're going to do is use an ice table after we've organized all of our information and determined which way the reaction is going to go to equilibrium. We're going to fill in this equation with values that are going to involve X. And then we're going to be able to solve. So let's do an example. Okay, so we have a flask that contains 1.66 atmospheres of nitrogen dioxide initially. And that's at some temperature. We always put that in there because the equilibrium constant is temperature dependent. And we'll talk about that more later. And the value for the equilibrium constant under these conditions is 0.125. So we want to calculate the equilibrium partial pressures of the two gases. So in other words, we're starting with all nitrogen dioxide. We're going to allow the system to come to equilibrium, and then we're going to calculate those equilibrium partial pressures. What will they be? So the first thing that you do is fill in your initial conditions. So this problem told us that we have 1.66 atmospheres of nitrogen dioxide initially. Notice that it didn't say one word about dinitrogen tetroxide. So that means it's 0. All right, so we just started off with nitrogen dioxide and 0 dinitrogen tetroxide. So if it doesn't mention it, if it doesn't give you an amount, then that means it's 0. Now, the big question is, what's going to happen now? How do we fill in the change line? And we're going to use a central concept to figure that out. And that is that there has to be at least some of everything at equilibrium. So at equilibrium, we're not going to have 0 of something. We might have a teeny tiny amount of it, but we won't have 0. And so if one of the reactants or products in the reversible reaction initially has 0, then the reaction has to shift toward that reactant or product, because we have to have at least some of everything. So what we're going to do is say, all right, some of nitrogen dioxide is going to react to form dinitrogen tetroxide at equilibrium. So how much? Well, we don't know. And so what we're going to do is subtract off 2x, okay? So minus x, and you're always going to multiply x by this coefficient. So minus 2x worth of nitrogen dioxide is going to react to form x worth of dinitrogen tetroxide. Now, I did put a 1 in here because that's the coefficient for dinitrogen tetroxide. Usually we would just write plus x, but the 1 is in there so that you can clearly see what we're doing. So now, after we have the change, and as I mentioned, it's really easy when one of the reactants or products is 0 initially, because it has to go in that direction. So that means you're going to add some. We're going to make some of it. So that's why it says plus 1x. And we're going to use up minus 2x worth of nitrogen dioxide. Now to get the equilibrium concentrations, we're just going to add up the initial plus the change. So 1.66 is initial minus 2x. So just going to add that up and put it in the equilibrium line. For dinitrogen tetroxide, it's going to be 0 plus 1x. Okay, so I wrote it very explicitly here so you could see what we're doing, but usually we would just write x there. Now, what do we do with this? So now we have expressions for equilibrium partial pressures in terms of x. And so now we're going to go to our equilibrium constant expression, the thing that we've been talking about but haven't used that much. And what we're going to do is plug in these equilibrium values in terms of x for the partial pressure of dinitrogen tetroxide or the partial pressure of nitrogen dioxide. Okay, so I'm going to take 1.66 minus 2x and I'm going to put it in for nitrogen dioxide. I'm going to take x and I'm going to put it in for dinitrogen tetroxide. And now we're going to solve for x. Okay, now this is going to turn out to be a quadratic equation, and so I'm going to go through and do a little algebra review with you. Okay, so we are going to use this value of the equilibrium constant that we were given. So remember, it was 0.125. And so we are going to plug in, we've already plugged in x and 1.66 minus 2x for our two gases. Now let's plug in the value for the equilibrium constant. Now we're finally ready to solve for x. Okay, so again, algebra review here. We're going to take this denominator, we're going to multiply both sides by the denominator. And so that's going to cancel out 1.66 minus 2x squared on the right side of the equation, and we're going to move it over to the left. And so now we have the squared term, the original value for k, and that's going to be equal to x. Now, we need to expand this equation, and so we're going to go ahead and do that. We're going to FOIL it out. 1.66 times 1.66, 2.7556. 1.66 times negative 2x, it's going to be negative 3.32x. We're going to do it again. Minus 2x times 1.66, that's going to give us minus 3.32x. And then we're going to multiply negative 2x times negative 2x, and that's going to give us positive 4x squared. So now we need to simplify this guy a little bit. So notice we have 2 terms here that are both in x. And so we're just going to add those together, and we end up with minus 6.64x. We're going to take this whole guy right here, and we're going to plug it back into our equation. So now that we've expanded it, we plugged it back in for that squared term, and now we're just going to distribute or multiply each term by 0.125. And when we do that, 0.125 times 2.7556 is going to give us 0.344. Multiply negative 6.64, we're going to get 0.83x. And then multiply 0.125 times 4, we get 1/2. And then we still have this x hanging out over here. You can't use the quadratic equation formula unless the whole equation is equal to 0 and set up with a, b, and c. So you have to collect all the terms. So what we're going to do is just subtract off this 1x from this side. So we end up with 0.344 minus 1.83x plus 0.5x squared, and that's going to be equal to 0. Now we're ready to use the quadratic equation formula. So again, I've labeled them a, b, and c. So a is always the x squared term, b the x term, c no x's at all. So let's go ahead and plug everything into this formula, and I'm not going to show that, but make sure you get these answers. So we end up with 0.199 and 3.46. So we get two possible answers. Now, one of these answers is ridiculous. One of them is not physically meaningful. Now, this value for x is the physically meaningful one. This one's way too big. So remember, we only had 1.66 atmosphere nitrogen dioxide in the first place. And this change would be much more than we even started off with. So it's not physically reasonable, so we're just going to throw it away. So now let's take 0.199, our value for x, and we're going to plug it in. We're going to go back to our equilibrium line in our ice table, and we're going to plug it in for x. And then we're going to add it up, sum it up. Okay, and then remember, this was just x for dinitrogen tetroxide, so we end up with 0.199. If we do this math here, then we end up with 1.26 atmospheres for nitrogen dioxide. Okay, now we can check our answer. So remember, if we have the equilibrium partial pressures for some system, the reactants and products in some system, we can plug those values into the equilibrium constant expression for that reaction. We can do that, and then we can multiply and get a value for K. So we can get the equilibrium constant value if we have the equilibrium concentrations or partial pressures of the reactants and products. And notice that we get our original K value back out of that. So that means that our answers are correct. We did our math properly, and we could calculate the same equilibrium constant value that we started with. Okay, next up will be heterogeneous equilibria.